Hello again, everyone. Welcome back to another statistics video. Today we're in section 4.2 talking about least squares regression. So in this video, I'm going to show you how to find the equation for the least squares regression line and how to use that line to make predictions. And I'll also show you how to interpret the slope and the y-intercept of the least squares regression line. Let's get started. So if you have a set of data for two variables and you've already graphed the scatter diagram and calculated the linear correlation coefficient so that you verified that the two variables do have a linear relationship, then we can find a linear equation that describes this relationship. The linreg command on the calculator gives us the coefficients for this linear equation, and this equation is called the linear regression equation. The regression equation also goes by the name least squares regression equation because this equation is found by minimizing the sum of the squared residuals. So now I know you're asking yourself, what is a residual? So let me show you. Here is the scatter diagram that we created in section 4.1, and you'll remember it was driving distance versus clubhead speed. So we have the clubhead speed here on the x-axis and the driving distance, the distance the ball traveled in yards on the y-axis. So for any x value, a residual is the difference between the corresponding y value and the y value that's given by the regression equation. So as an example, let's take this data value right here, 103,274. You may remember that in our table of data, there was one swing where the speed of the club head was 103 and the ball traveled 274 yards. That is an actual observation. Now the regression equation predicts that when the club head speed is 103, the distance the ball travels will be about 269.3 yards. So that's obviously a little different from the observation that's recorded in the data. This difference between what the regression equation predicts and what was actually observed is called the residual. So what the regression equation does is it minimizes the sum of the squared residuals for all the points. See, every point has a residual unless it's right exactly on the line. So the regression equation is the one line that gives us the smallest possible sum of the squared residuals. So the regression equation is the line that fits the best in the dots made by the observations we actually recorded. And for that reason, sometimes you'll see this called the line of best fit. And one good thing to know is that the linear regression equation will always go through the point x bar, comma, y bar. So if you take all the x values in your data and find their mean, you'll have x bar, and if you find the mean of all the y values in your data, you'll have y bar, and the regression equation always has to go through the point x bar, comma, y bar. Now since the regression equation predicts possible y values and it doesn't calculate actual observed values, the regression equation is usually given by y hat equals ax plus b. So it's just a y with a little caret symbol over it, and when we read this we say y hat. The hat is there just to remind us that the y value is a prediction and not an actual observed value. Now we're going to take this table of data that we had from section 4.1, I'm sure you remember, and we're going to get the calculator to find the linear regression equation for us. Now this is another place where it makes a difference whether you have the new operating system on your calculator or the old operating system. So I'm going to go through it twice, and I'm going to do the new operating system first and then the old one. Of course, the new one is a little more convenient and the old one not as much because that's progress. But let me just start here with the new one. So to get the linear regression equation, all we have to do is put our data in the appropriate lists and then press Stat, arrow over to Calc, and then what we want is option number 4, so that's linreg. You could arrow down and press Enter, or I like to just press the number And if you're on the new operating system, you'll get this linreg wizard. So you just need to tell it where your X numbers are, of course they're in list 1, where your Y numbers are, of course mine are in list 2, and for frequency list we need that blank. So arrow down and press delete, so that's empty. And now on the line that says store reg EQ, it's asking us where we would like to store the linear regression equation. You can just leave it blank and it won't store the values anywhere, but if you think that you're interested in graphing this line, then it might be convenient to tell it to store the numbers in one of the Y variables. So I'm going to go ahead and do that here. If I arrow on down to that line, I would like to tell it to store my linear regression equation in Y1. That's one of the Y variables that the calculator can graph. So to access that, I press vars, which is short for variables, and I arrow over to Y variables. I want to store it as a function, so press enter there, and just Y1 is fine. Okay, so that's good. And then let's arrow down to calculate and press enter. And we are familiar with this screen because this is the screen where we got our R before, and you'll remember that this is what we got for R. Now it's telling you here that the linear regression equation is going to be y equals ax plus b, and they're giving us here the a and the b. So our linear regression equation would be about 3.17x plus negative 55.80. And that's just rounding off to 2 decimal places. You should watch in MyLabs Plus because they'll tell you how many decimal places to round off to. There's not really a rule about it. We'll just follow the instructions that they give us. Now let me go back and talk about the old operating system. So if you have the old operating system, then when you press Stat, Calc, and do option number 4, you don't get that wizard screen. You just get linreg ax plus b. Just like we saw in section 4.1, if you don't tell it which lists to use here, it will assume that you want to use L1 and L2. And that's where my data is, so that's fine. But if your data were in 2 other lists, you would need to put, for example, list 3, comma, list 4. I'm going to leave it blank because my data are in list 1 and list 2, and I'm just going to press enter. But now notice that it did not ask me where I wanted to store the linear regression equation. So there is a way to have the calculator do it automatically, but honestly it's probably easiest for you to just jot these 2 numbers down and type them into the y equals screen yourself. And I'm going to do that now. So what we're going to do is press y equals, and notice it gives us all of these graphs we could put equations in. I'm just going to use y1, and I'm going to enter 3.1661 because I jotted this down from the last screen, and then the x. So it was ax plus b. So ax plus negative 55.7966, but instead of saying plus negative, I'm just going to put minus. You know that's the same thing. Minus 55.7966. And we'll press enter. And now let's graph. And when I press graph, notice that I really can't see the line or my statistical data at all. So I'll need to zoom in on the statistical data. So I go zoom, option 9. Remember option 9 is zoom stat, so press 9. And here are our dots, and here is the line of best fit, or the regression equation that goes through the dots. Now if you don't have the regression equation stored in one of the y equal variables, then you won't get the line, you'll just get the scatter diagram. Okay, just to recap, the linear regression equation that we just got from the calculator was y hat equals 3.166x minus 55.797, or you could say plus negative, but you know minus is the same thing. Now we want to be able to use this linear regression equation to make predictions for other x values. So now we're going to use the equation to predict the distance a golf ball would travel if the club head speed is 104 miles per hour. So what we do is we plug the 104x value into our regression equation, and that will give us a prediction for y. So we say for an x of 104, y hat equals 3.166 times 104 minus 55.797, and if you put all that in the calculator, that gives you about 273 yards. Now you may remember from algebra that for a linear equation in the form ax plus b, the coefficient of x, in this case a, is the slope, and b is the y-intercept. And you also may remember that the slope refers to the steepness of the line. The sign of the slope tells us whether the line goes uphill to the right or downhill to the right. A line with a positive slope will go uphill to the right. A line with a negative slope will go downhill to the right. The y-intercept is the point where the line crosses the y-axis. This is also the point where x equals 0. So to interpret the y-intercept, we must ask two questions. One, is 0 a reasonable value for the explanatory variable? And two, do any observations near x equals 0 exist in the data set? If the answer to either of these questions is no, then we don't attempt to interpret the y-intercept. For example, in the golf club head speed problem we've been looking at, x equals 0 does not make sense because remember, the x values were the club head speed. A club head speed of 0 would mean that the club is not moving and therefore could not hit the ball, and therefore no distance would be achieved. So we do not attempt to interpret the y-intercept for this data set. Also keep in mind that the regression equation can be used to make predictions, but only within the scope of the model. For example, in the data set we've been looking at, the x values ranged from 99 to 105, so we would not want to make predictions too far outside of this range of x values. For example, we would not want to try to use our regression equation to predict what would happen when x equals 120, because our data only promise us a linear correlation from x values of 99 to 105. We have no observations to show that the correlation continues past an x value of 105. It may be that if the golf pro had continued his experiment, he might have seen that for higher club head speeds, the increase in distance sort of drops off like this. We don't know because we don't have those observations. So just be very careful about using a regression equation to make predictions that are outside the scope of the data. When somebody makes predictions that are outside the scope of the data, that's called extrapolating, and it often leads to really silly and erroneous conclusions. Now let's look at a new set of data. So here I have a table with the weight of some different models of cars and miles per gallon for each of those cars. And the problem says an engineer wants to determine how the weight of a car X affects the mileage Y. The following data represent the weights of various domestic cars and their miles per gallon in the city for the 2011 model year. Find the linear correlation coefficient and determine if the correlation is strong enough for the regression equation to be meaningful. Now I want you to keep in mind that you can always put this data in list 1 and this data in list 2, and the calculator will always give you a linear regression equation. But the calculator does not know whether the equation is worth anything or not. We have to be the ones to decide that the equation is worth something based on the linear correlation coefficient. And remember, we had table 2 from Appendix A that would tell us whether our linear correlation is strong enough for the number of data values that we have. So of course we'll use the calculator to find the linear correlation coefficient for us. I've already entered the x values in list 1 and the y values in list 2. And now to find the linear correlation coefficient, you remember that's R. So we will press Stat, then arrow over to Calc, and then it's option number 4. And then This is the old operating system. All I have to do is press enter. Remember, on the new operating system, you just need to make sure that where it says frequency list, that's blank, and where it says store reg EQ, you don't need to store it anywhere for right now, so that's fine. So we'll just press enter here, and I see that our R is negative 0.9596, so that's going to round to negative 0.96, and to determine if the linear correlation coefficient is large enough for this linear relationship to be meaningful, we just need to go to table 2 in the book and compare the absolute value of our calculated R to the value in the table. And I've already looked in the table, but you can look too. And for 11 data values, the required R is 0.602. So we've got that beat by a lot. So our linear correlation here definitely is strong enough. And so now for part B, it says find the least squares regression, treating weight as the explanatory variable and miles per gallon as the response variable. So that just means that the weights belong in list 1 and the miles per gallon belong in list 2, and that's the way we have it entered. So we can use the A and the B here to get the regression equation, and I can't write it down while I'm in calculator mode, but I'll go ahead and tell you that it's going to be y hat equals negative 0.0069x plus 42.907. So you just use ax plus b, where the a comes from here and the b comes from here. So here's where we are. We just found that r equals 0.960, and we said that this would be a meaningful linear relationship because our table only required an r of 0.602. And we had that beat. So that tells us we can use the linear regression equation to make predictions. And we found a linear regression equation of y hat equals negative 0.0069x plus 42.9068. And it says interpret the slope and the y-intercept if appropriate. Okay, well, let's do the slope first. Since we see that the slope is negative 0.0069, that means that if the weight increases by 1 pound, the total miles per gallon will decrease by 0.0069. So I'm going to say MPG, miles per gallon, decreases by 0.0069 for each weight increase of 1 pound. Now, the y-intercept is 42.9, but let's think about whether it would be appropriate to interpret the y-intercept. Well, the x values represent weights, and if x equals 0, that means the weight of the car we're considering would be 0, but a car that has no weight cannot exist. So it would not be appropriate to interpret the y-intercept in this case. Okay, now continuing with this example, it says if a particular model of car weighs 3,550 pounds and it gets 18 miles per gallon, is that mileage above or below average for cars of this weight? Well, let's take our regression equation, and we know that this can be used to predict miles per gallon if we input a weight. So let's go ahead and plug in 3,550, and then when you run this through the calculator, you see that the predicted miles per gallon is 18.4. If this car is only getting 18, where our regression equation predicts 18.4, that means the actual observed mileage for this car is a little below average. So it's just a little on the low side. And then it says another model of car weighs 6,000 pounds. Can the regression equation from part B be used to make a prediction about its gas mileage, and if so, make the prediction? Well, if you look back at the data, you'll see that the weights in the table range from 2,605 to 3,860. So 6,000 is well outside the range of this data. Therefore, it would not be a good idea to use this regression equation to make a prediction of a car with a weight of 6,000 pounds. And then the last part, it says the third model weighs 3,825 pounds. Can the regression equation be used to make a prediction, and if so, make the prediction? Well, yes, 3,825 pounds is within the range of our data, so our linear relationship does hold up here. And let's just plug our value of 3,825 into our regression equation. We'll get y hat equals negative 0.0069 times 3,825 plus 42.9068, and we come out with about 16.5 miles per gallon.